Welcome to the office. We want to continue taking a look at direct products today. So considering our previous definition here, that of a Cartesian product, what we want to do is we want to add in the detail that each of these sets has a binary operation and is a group. So instead of saying S1, S2, all the way up to Sn, if we have G1, G2, all the way up to Gn, what can we conclude about the Cartesian product? And of course, we're desiring to conclude things within the idea of group theory here. So is it a group is the question. And indeed it is. And that's precisely what our next theorem is. So if we have these n groups and we take their Cartesian product, so here's an element within the Cartesian product. Here's another element right? That's the Cartesian product. We want to define the product of those two elements. Okay, so we have the Cartesian product, and we are taking the product of two elements inside of that Cartesian product. We can define that to be simply the combining of these. Now, right, A1, B1, A2, B2. This might look really familiar to you in terms of if you were to take two vectors, for example, right, which is an ordered n tuple. So if I were to take 1, 2, 3, how could I combine it with 3, 0, 4 to create something that I am just taking the product of those two things. So I was thinking dot product actually, but then I just realized that dot product has you add those things together. But 1 times 3 gives you 3, 2 times 0 gives you 0, 3 times 4 gives you 12. So it's not really the dot product, of course, because you're not, sorry, I wrote this as 3 times 4. That would be better. Dot products would add those together, whereas we're not adding them. So this is 3, 0, 12 here. It stays as 3 entries. All right, so the idea is that we take each of these elements, we multiply them, and ta-da, we have something that is ideally back in that Cartesian product. Right, each of these things should be back in that group. And the question is it? Well, of course it is, right? If I take two elements from group 1 and I multiply them, then it's still in group 1 because group 1 is closed. We also know that group 1 is associative, and we know that there is an identity and that there are inverses. So we can pretty easily verify that the Cartesian product of groups is in fact a group itself. The operations here are all written as the same thing, multiplication, but we should recognize that the operations might actually be different. And the example that we consider below, that's what we'll see. So again, Cartesian product of groups, combine them in this way. The Cartesian product is a group, and it is called the direct product of the groups. So this theorem provides for us that definition. All right, so again, feel free to verify. It's pretty straightforward to verify that this is a group. What I'd like to do is I'd like to take a moment to just say, all right, well, what does it look like for us to take the Cartesian product of two groups and then try to combine these elements appropriately. All right, and I want to make sure that I do this well, so I'm going to try to grab onto our notes that share with us the multiplication table for S3. All right, I was able to grab onto the table for the multiplication table for S3 here, which we had developed in an activity previously. All right, so we want to list the elements in this Cartesian product of S3 and Z2, then consider the product of pairs of elements in this direct product of groups. So if I take S3, I want to recognize that, of course, I could write that as a collection of permutations because that is the permutation group. However, this is equivalent to D3, the symmetries of a triangle, and that's where this particular notation comes from. So we have 6 elements in this group: row 0, which is the identity element; row 1, a rotation; row 2, another rotation, and then we have the symmetries, lens or the reflections, that is mu1, mu2, mu3. And of course, Z2 has just the elements 0 and 1. So in the cross product, there are quite a few elements here. If I take S3 and I cross that with Z2, that's going to give us 12 elements. So let's try to list those out. Row naught 0, row naught 1, row 1 0, row 1 1, row 2 0, row 2 1. And let's see here, move on to the reflections. Mu1 0, mu1 1, mu2 0, mu2 1, mu3 0, and mu3 1. So that gives us all of the elements in that direct product. Now I might want to observe that the, let's see here, the identity element, identity element is just the element that contains the identity of both of these groups. So row naught 0 would be the identity in this case. And if I wanted to, this is where things get a little bit weird. So multiplication is the usual representation. If we're just talking about direct products of these sorts of things, so Zm cross Zn, then it's quite often that they use addition notation, because addition is the operation within these particular groups. Here, it's like all over the place, right? Technically, this is composition of functions, and this is addition modulo 2. So they're completely different operations, and that's perfectly acceptable. Notationally, we would still write this as, let's see here, we could find the product of row 1, 1, and mu2, 0, for example. Well, according to our definition, that's just row 1 mu2, comma 1 plus 0, right? We combine using the appropriate operation of the group. Row 1 mu2, well, I don't know that one off the top of my head, so I'm going to have to come over here and say row 1 mu2 is mu1. Fantastic. Mu1, and then 1 plus 0 is 1. So we're able to combine those elements. If I wanted to, I could find inverses, right? So the inverse of row 2, comma 1 should be, the inverse of row 2, I believe, is row 1, and then the inverse of 1 is 1. So row 2, row 1, and then 1 plus 1. And this results in, now I'm certain this is the identity, right? Row 2, row 1. But if we're curious, let's just go take a look. Row 2, row 1, okay? Row 2, row 1 gives me this. That is the identity element. Row naught. And 1 plus 1 is 2, but 2 modulo 2 is 0, the identity element. So we have inverses can be found as taking the inverses of the individual elements, that sort of thing. All right, so I think this should give us a pretty solid idea of what it looks like to take a direct product and then combine elements within direct products. That's all that I wanted us to see in this video, so I'll see you guys back in the office in just a little bit for more on direct products.